I'm a pre-sales guy for Vectra. I've been one of the first guy in Europe actually, and I'm leading a team of very cool people today. And Daniel invited me for this event, and I'm super happy to be here with you. Whenever we discussed about what we were going to do today, I think it was two main topics that we thought would be interesting. The first is giving you, first of all, an introduction on Vectra, because some of you never heard about what we are and what we do. But the intent really was to give it kind of a technical session on a few topics, right? The first one being AI, and the second is hacking. So today we'll do kind of two parts of a session. The first will be what is Vectra and eventually what is data science and how we use it to do things. We'll see what it is. In the second part we'll have a break, and the second part will be a live hacking session when we'll go through a sequence of an attack, which is actually a reproduction of what we have seen at at one of our customers. That I put into a machine here to kind of a lab. And so I'm going to show you eventually what we see and what the product is able to find. Okay? So that's just the intent for this session this morning. All good? Cool. The first thing, right, and the reason why we exist is probably comes from an interesting story. Back, I don't know if you know Mr. Robot, the TV show, right? The guy that actually has been writing the technical hacking of Mr. Robot is actually the founder of Vectra. So what happened is this guy is kind of a hardcore hacker, and he thought that product like IDS's product and so on were actually pretty weak, right? And he had an exchange, right, with different organizations, decided to create his own company. He did a kind of a free people type of show where we use AI to do stuff because AI is very trendy. It's probably like, so take a couple of PhDs and try to understand what you could do with them, hack something away. And then he was joined after a year or so by a guy that was working before with Aruba. And at the time he was a COO of Aruba. And he had one of the largest social media company in the world that just been hacked. And they were hacked using the Aruba Wi-Fi, right? And the CTO of that company and CIO of that company said, like, you have seen that traffic, you should be able to tell me. It's like, that is true, I'm going to make a company. And eventually found that hacker, and just like, together we are going to build something which is, let's find the bad guys in a network. What was very apparent then at the time is there is it was back 7 years ago, right? And one of the things that was very clear is you had more and more payload being created and malware being created that were pretty unique. And at the time, back 7 years ago, it was like hit rate on antivirus software like 50-50, right? Maybe you detect, maybe you don't. And also it was the beginning for seeing machines like iPhone and iPad and so on when you have no agents installed on them, right? So the question is like, if you want to find the bad guys, you've got to think about everything is 0 day. And you've got to think that you cannot rely on signatures anymore because they're just never going to work. So it's kind of the thought process that they had. They're like, well, it's going to be pretty simple then. Let's build a tool that will allow us, from a network standpoint, whoa, stable, stay with me. So it's like, what is interesting, right, if I look at whenever I discuss with a customer, actually I had a very interesting discussion last week where a guy is like, I've got about 17,000 machines in my network. And I was like, no, you've got 87,000. Like, no, I've got 17,000. No, look, my machine is telling you that you've got 87,000. So some people have absolutely no idea, and what was scary, it was a bank. And I think it's going to be an interesting session. Maybe I should stay like that? Okay, let's do the big reset, right? And so the problem really is like, most of the time there is a big challenge in terms of network visibility and what people really expect to see on the network compared to what they really have. So the idea of Vectra is like, okay, let's make an assessment of what you have and let's try to focus on the bad guys that come. We eventually have in our team a guy that really loves printers to a point that he found a zero-day bug in Microsoft like 2 years ago. That was actually a bug allowing remote access to machines from Windows 3.11 to Windows 8.1. Right? Just like, yeah, he found that you could push some drivers automatically as a root admin. So just saying, hey, I'm going to install a driver on remotely for the printer. And just you could do remote code execution. So, and it was very apparent that probably that was kind of an attack vector that we never thought about. Who of you is protecting your printers? Like, not that much, right? What is interesting is whenever you have a printer with a USB stick, right? Whenever you plug it, you can actually most of the time execute PostScript scripts to be able to spoof the memory of the system and to install your malware, custom drivers and so on. So whenever the next people come and print something, your malware can propagate. It was eventually one of the techniques that our guy used to hack some organizations, like three-letter organizations from the US government and that type of stuff, right? So the idea is really what we do is, and Vectra is over 300 people now, and what we really do is like, okay, let's try to do something on the network that will allow us, without an agent, to be able to see the progression of that attack. Talking about that printer attack now, but there are many surface and many attack vectors. And let's try to figure out what is the most interesting way to do it. Right? So if I look at that problem statement, which is, I need to find the bad guys. I know that I've got maybe 17,000 agents when I've got maybe 80,000 machines. So I've got a massive gap in terms of coverage. How do I solve that? The first thing is like, hey, we are going to make signatures. Everybody does it. Maybe we can be more clever, but eventually we will never be able to. But the truth is, and it's interesting because if you look at Gartner, Forrester, and all of these analysts, like IDS is dead. The stuff, you will have to write so many signatures on daily basis. I think Snort has more than 40,000 of them. That you will not be able to have any sort of good coverage, and what you add is just additional noise. So that cannot work, right? In the security analyst landscape, right, on the security landscape, there is a 373,000 job open for 200,000 people trained. Finding people that are security analysts that do find stuff, that are able to create rules, is pretty rare. So the question is like, okay, we need to think about to create some sort of solution or product, or solution to a problem, which is there is 200,000 malware created per day. Most of my problem is I've got no coverage. And at the same time, I cannot create more alerts because I don't have people being trained on it. Right? So that's what we thought. So signatures, more false positive, it's never going to work. Then, whenever we build a product like, hey, there is that super cool tech that exists, IPFix NetFlow. We take the traffic from the switches, we bring it to us, and then we're able to run analytics. The problem of that is like, it's very high level values. Right? So you take a data sample, 1 out of 1,000, you get some statistics about it, and you miss a lot of things. So reconstructing that would make no sense. One of the interesting statements also, and one of the things that I've seen in the recent days, I've got few of my customers that disconnected their SIEM. They're like, okay, I came with a SIEM, set up the stuff, spent 3 years on it, created 3 use cases, and never found a single bad guy. Help me. Right? It's great for my compliance need, but I've got no idea what's going on. So for example, I've got a company that I work with. They've got 3 people. So they made a correlation rule on their SIEM saying, every single time somebody uploads more than 100 meg of data into some cloud stuff, send an alert. They got 1 alert every 7 minutes. So they got people calling, and they had like 3 dedicated people just making cold calls to people and say, hey, you've tried to upload a file. That's bad. And so like, great job for these 3 people that have a job, right? But honestly, they stayed in that job for like 3 months, 4 months, and then they leave. their job is every 21 minutes, because they are free, right? They got to place a call and say, you've done something bad, mister. Just, you know, what is the data that you've done? And it's the only thing they ask. There is no intelligence, there is no nothing. But that was the use case that was defined. So how can we be more clever? Right? That's really the point. There are actually very interesting use cases in CM, right? Don't get me wrong. Eventually, the other challenge with CM is if I look at a company like Logarithm, for example, or some of these guys, like, hey, I've got 40,000 use cases for you. You can install 40 of them. Which one do you pick? Right? And it's the other challenge, like, yeah, I've got many problems that I can solve, but I give you the choice to do whatever you want. But I mean, it's your security posture. It's your security which is at risk, right? It cannot be that you make the choice out of 1 out of 1,000. So it's just like, okay, good. Eventually, we could go with all network traffic, right? But that is a crazy amount of storage to consider, right? There is a very large pharmaceutical company that spends about 4.7 million a year into network storage, into storage to store the network metadata. Amazing for the disk vendor, but it's not really working. So what we thought is like, okay, we need something that gives us good visibility and coverage, able to store a lot of data, but at the same time, take the data that matters. The question is like, what is the data that matters? And that's the discussion that we have with our data scientists, right? What do you need to find the bad guys? So what we did, like, okay, what would be great if we could get all the data and we filter out what we need. What we need is like Kerberos traffic, it's DNS traffic, it's HTTP traffic, it's SSL certificate that can be extracted. So eventually we take that data out and we bring some additional context. So part of what we call data enrichment is we consider that things are based on machines, host, it's not an IP address, right? The machine can have many IP addresses on the wireless, on the wire, on VPN connections. It's still a machine. So we enrich and say, well, that machine does weird stuff. And then what we do is we analyze kind of in a smart way the data, right? And that's the talk, and that actually would be the second part of my discussion. It's like AI, right? The problem is like everybody does AI, so I hate to have that talk. So I'm coming here to talk about AI when it's a terrible topic. Because, I mean, if I look at every single security vendor, they do AI. They do very poor stuff, and it's very sad. But eventually, it's a very frustrating discussion, right, for me. So I will show you definitely why we are very different from these different companies. Yeah, but the point and really what we want to do is we want to find the bad guy. That is our core mission. The rest don't matter. And eventually we find a lot of bad guys, which is the good news as well, right? One of the things that we did, so finding the bad guy is great. Having the right data is great. And it allows you to solve 2-3 types of problems. One of the first problems is like, okay, you find the bad guy, so what? I've got an initial problem, I have an initial detection. I tell you, here, you've got that person that did all these activities overnight. So yesterday I was a customer. We had some weird IP addresses from Russia that just dump a full database overnight of something that I want to tell you. I don't want to tell you, but like the full data and customer base was owned overnight. It might be in the news in a couple of days, but that's, whenever you look at, you probably heard about that company called Saudi Aramco that had been just bombed, and that actually had a massive price petrol difference, right? That impact on petrol. It's actually one of our customers. I was on site to help them finding the bad guy that actually stole their stuff, right? So there is, outside of all the things you see in terms of war, there is always a cyber war behind. So we help people with that. And the problem that all of these companies that tell us, like, yes, you got the initial thing. What about you give us all the data so we can also do some incident response and find the attack chain, right? Because yes, I've got the first scans, I've got the first dump of data, I've got my command and control activity, and you detect it. But eventually, what I'm interested to see is like, what are the other machines which might be impacted, or what all these the whole data and what this machine is doing. And so what we've done is we expanded a bit that idea, like finding the bad guy. And so eventually we give also the capability to store the data into a SIEM and all of the metadata, so you can look for it, or into a cloud platform that we provide, and you tell us, instead of having to maintain a SIEM, which is an absolute pain, we do that for you, right? So we provide you a kind of a SIEM as a service for all data. And then, for sure, we use our AI stuff to be able to find the data. In order for you to search for the data, we formatted that into a standard open source Zik format, or BRO, that's the name of that tech, in order to have kind of a well-documented structure of data. We actually don't use Zik at all in our product, right? So we have a tool that forward the data to a Zik format. What is interesting with that metadata, right, is on top of the Zik format, we enrich it. So for example, the popularity of the IP addresses of the users. So you have some admins, they'll connect to specific admin ports to manage some machines. We tell you, well, that guy is probably a very dangerous person in your organization, and somebody that is potentially at risk, right? If somebody steals that credential, that can be trouble. So we enrich that data, right? And we store that into the system and say, that account at very high privilege connect to all of these RDP machines and all of these SSH available services. And suddenly the account is used to connect to something completely different. And probably the account was stolen, right? And so we enrich that thing. Very simply, what that platform does, it allows you to search and hunt for the data, right? So it's based on an Elasticsearch Kibana infrastructure, so pretty known type of tech. The richness for us and what we solve really as a problem for our customers is like, hey, Elasticsearch is a very fragile product, right? I don't know if you run it or if you have built data lake on your own. I've been out of curiosity for myself trying to build that stuff. It's whenever your query is too complex, you eventually ended up breaking your full data lake, right? So the system just completely fall apart, the memory goes off the roof, the system crashes, it takes you 2 hours to rebuild. It's a nightmare. So we actually have come up with a very stable version of that data lake. The other thing is, for sure, we've got that product called Detect. The idea for me is to give you a demo of that, so you got a good understanding of that eventually afterward. The point is really how I help you prioritize also the search for saying, well, out of the millions of alerts you might have received per day, how do I give you maybe one alert per day that is meaningful? Right? So you have 10,000 IP addresses in your network. I might give you one alert per day saying, maybe you should investigate. Right? So the signal to noise ratio of our product is pretty strong compared to what you have with a standard IDS or maybe anomaly detection products. We have a lot of people that we work with on a daily basis, and we really want to integrate with many people because we know that you already have a lot of tools, or some at least, maybe from that list. On daily basis, that is growing, so we start to have integration with Checkpoint, with all NAC vendors you can imagine, all switching vendor as well, because sometimes just want to have ton switches as well. So yeah, we just expand that ecosystem. So just to summarize, the way we work, we are a network sensor that can be installed in different places. So the standard, buildings that we are in today, in the data center as well. And we see a lot of people having a desire for coverage in the cloud. So we have sensors for the cloud as well for the people that made that migration already. The company is pretty nicely recommended by our customers, right? We have a very healthy customer base today of people that just tell that they love our products, which is always a good thing to have. We take the time every quarter to be with every single of our customer to make sure that they are okay. And I think that is a very important part of what we do, right? Outside of selling you a product, we're there with you. We help you just making sure that whenever you have questions on detections and so on, that our team of analysts is also there to help. Questions? Oh, come on. No? Okay. Then I've got two options, right? The first is little demo. So you understand out of what I'm just saying that that's kind of real, and I can go through a quick attack chain, probably in 10 minutes, if it's okay. And then we can go and discuss a bit in detail about kind of AI. And whenever you discuss with vendors or people that tell that they have AI, what you have to consider, and eventually what we consider when we develop our stuff. So that is our UI, right? So whenever you connect in the morning, you wake up, and then you not knowing that interface, you probably were like, ooh, I've got critical things, right? So this is a lab that we have in our premises in the US, which is a reproduction of everything that could go wrong, right? So some weird malwares are running down there, some advanced attacker simulations are being done as well. But more or less, if I look at our products, like, oh, I see that something is wrong, right? So one of the things we want to do is the training time on the product should not be more than 2 hours. That's really the focus we have, because we know that the people that are going to use that product are going to be probably junior analysts or people that have very limited knowledge on security overall, right? So we need to just have a super simple product that solves the problem of, hey, I want to find the bad guy. Not being an expert, right? I'm going to click on something on top of there. There are 3 buttons. Which one do I pick? I've got option number 1, Leroy. Option number 2, that weird stuff going on here. And option number 2, Cindy. So Leroy, Amazon, Cindy, where do we go?
Let's take the goal.
So Cindy?
Yes.
Cindy. So Cindy is actually was a real user. That was part of I think it was marketing group, right? Cindy has a machine. It's a Mac, so we figured out that it's a Mac based on the network fragment, so no need to do anything but just looking at the data, right? And what's interesting with Cindy is the first thing we observed with her is we had this weird use of her account, right? So in Vectra, the way we try to present it is like, well, instead of showing individual events, we show you the machine and all the bad things that machine did. We have 3 main things that were done. The first is Cindy is trying to connect to weird things that she's never been connecting before. And then she's trying to find different file shares on that specific file share service that they're trying to connect, and then she's stealing data. So it's a typical case of an insider, or an account may be stolen, where Cindy does a lot of bad things. So let's try to figure out exactly what else she does. In order to simplify the analysis, right, we try to map it to the kill chain, saying, well, there is reconnaissance, and there is lateral progression, and there is an exfiltration happening at the end. The first thing we observe is we have this weird use of our account. So if I look at what Cindy does, or what this account does, we define for every account and every machine and every host and every service which is being accessed kind of a map. And we say, okay, that's my baseline. So that's part of the different algorithms we have in the product. And so for everything that is being done in the network, we kind of record that, and the algorithm learn about it. What is interesting, right, is if I tell you what that is. Can you tell me what it is? Fast. What is it? It's a phone. How do you know?
Because I see it.
Yeah, but how do you know? I mean, you're very far. Which phone is it? And that's exactly my point. So you have a pure AI in you. If it was a signature, you will know that that's an iPhone, 7 or 8 or whatever, right? And you will have the signature. You will be able to tell me exactly what it is. I just show you that stuff very fast. It's like, what is it like? And I could have been doing very much the same, right? What is that, right? It was like, well, that's a clicker. How do you know? Because the way I interact with it, because of the shape of it, because of the way I hold it. So what our data scientists do is just they analyze these parameters. Right? They figure out, well, that's black. Most of the phones are black, or they are a big, pane of glass that looks like a screen. And they define what we call features. And they record these features. A more interesting feature, instead of looking at the look of the phone, is probably that he uses some radio frequencies on different segments of the network, of the radio. And there are people interacting with it, and there is a correlation with people interacting to traffic being released. Right? That could be kind of a better way to define a phone from a technical perspective, right? That's exactly what happened here. So we define that baseline, and we learn it. Very much what you have right now, you've never seen that phone, you will never see it again, or well, probably will meet again, so you will see it again, but you will not know exactly which phone it is. The difference between AI and signatures is you don't know which phone it is. You've seen it before because you've seen so many phones. The next phone you see, no matter what is the brand, no matter what is the company, you know it's a phone. You might not know which it is. This is what we do. Right? So the system learns a feeling and regroup things, saying, well, the norm of that machine and that user is that specific realm of things, connection from 6 in the morning to 10 by night on different services and different machines. And we define what we call the baseline. And then whenever you see something weird in the future, because it's kind of nicely regrouped, you would say, hey, that's my phone. And what is interesting is part of what we have learned from Cindy. And the account that she's using, Cindy at corp.example.com, of course it's anonymized. We couldn't tell. Actually, it's not Cindy, her real name. But really what we have is, we know that people that connect to the SQL database are usually people coming, which is HQS Service Act or Bob Admin or Web Service. That should be it. Why is Cindy connecting to that? That doesn't make sense. What happened is actually Cindy figured out how to steal certain accounts, figure out that she can have a certain level of privileges that she shouldn't have. When this account is stolen then, the next thing that Cindy did is she is then able to just say, hey, actually it was an administrator account that was being dumped. So she connects to the SQL server, figure out that maybe use Mimikatz or whatever, this tool to dump some memory, extract an account which is administrator, and use that administrator account to mount some file shares on the different servers, right? So typical case, I have one of the largest pharmaceutical company in the world. These guys, like, she finds something interesting. She downloads these interesting files, which is not that much, right? 250 meg of data. And she sends it to somewhere. Part of the algorithm and what they do is they record all sort of traffic that has been observed from the some machine to kind of a middle machine, which is the Cindy's Mac, and then an upload to a cloud. So it's kind of, I grab stuff and I send it somewhere else. Right? So that instead of trying to just have every 100 meg of data, somebody calling in, that's a much cleaner way of solving that problem, right? Let's try to figure out if somebody moved data around. One of the reasons why we created that algorithm, it's very unlikely that a hacker get access to a machine that has the critical data. So you will have data moving around the network at some point, and some of this data transfer. That's why we developed this type of algorithm. Make sense?
That's great. You check the data itself?
No.
In that case, how can we ensure that the data extracted from the SQL is the same which has been uploaded?
We have no idea.
In that case, it can be two separate actions.
It can be absolutely separate actions. The system is done well enough, so the amount of alert you will get of that, for example, will be in the realm of 1 every 5-6 days, right? Maximum. It's important to know that it's there, but if that machine has just one alert, it will just not be in such a critical state. One of the philosophy that we have in the product is a hacker will do multiple steps of an attack. And let's say if I look at a global attack, right? So Cindy, for example, the first thing she does is she's doing this account dump. So the machine will be kind of here, you know, because it's critical for you to know that an account has been dumped. Actually, it's the first, you know, step of something which is a high risk for you. As soon as Cindy's trying to do file enumeration, because it's the second step of a kind of a logical progression of an attack, we will move Cindy into that critical quadrant. And because on top of it, she did an enumeration, which is like, poof, she goes there, right? The idea is there are many of things that are happening down there that you shouldn't really care about.
What about the timing? I mean, sleep there for 2 weeks.
So
after the first part of the attack, then sleep another 2 weeks, and then do the second
that's exactly what we observe. So we have many situations. Yeah. So if I look at a very advanced attack, I mean, you have to imagine that bigger is the threat, longer the attack will take, because they will remain very silent, and it will be a very few activities, I mean, per day. And it's always super targeted, as silent as possible. It's a very interesting. So whenever I've got a pen test, in 10 minutes it's up there, right? Because it's super easy to find these guys. Whenever I've got a more kind of silent attack and some government fighting other governments and type of thing, probably would take 3-4 weeks to get some alerts up there, right? Still, before the exfiltration, it might take 3, 4, 5 weeks and more before you get there.
But you correlate all of this.
But we correlate that. So eventually the machine will be, poof, there is a big alert, nothing for 2-3 weeks, so it will down, because we rank that based on the time to which it's observed, and then there is something else, which will just spike again there. So we've got kind of a very living, well, question? Good?
About the data, you said that you don't check the data itself,
Mm-hmm.
you check the amount maybe, or you just check the steps taken.
So looking at the amount of data,
Picture upload.
in the case of the data smuggler is exactly what we do, right? We just look at the amount of data. But for many other algorithms, it's not sufficient. So let's take another example, right?
For example, just filling a Word document with a contact template, copy the text, and just send out the text.
Then that's something that we will not detect. Just to be very, very clear, we will not detect that. Also because before you get there, it will be a lot of other things. I mean, and then I will show you in my demo, actually, I steal some things like that, which is very low data. The product doesn't detect anything. But there is a lot of things, like an ongoing command and control activity, there is overscan, there is maybe other type of discovery, there is maybe dump of things that you know, are critical. So that's what we will tell you. So that's the first thing. The second question I have usually is like, hey, but what about the things you learn, and there is already an attacker in there, and the attacker is just trying to steal data already, right? That's the kind of next logical question, like, you learn wrong. And yes, we do. But it's fine, because if an attacker already stole your data, end of the game, you already won. An attacker which is in your network is always going to progress. He always wants more. He always will move. And that is the move that we capture, right? So that's the... And in terms of the data that we store eventually, so here you see another view of an attack, right? So it's a more orchestrated attack that you would have here, where I've got a command and control activity from one machine that propagates something to another, to another, to another, and then data are being stolen. And what we do is we create that map and that vision of the progression of the attack. So whenever you've got something wrong ongoing, you know. Then, as you know, I found that weird guy on my network, there is a few things that is doing, like a strange tunnel. So I don't know if you're familiar with tools like Metasploit or before PowerShell Empire or Cobalt Strike and all of these tools. But more or less, it's a post-exploitation framework. So you're being infected, and then they've got full access to everything you have. Most of the time, it's hidden from your antivirus software because it looks like fully legitimate activities. Such as, hey, I'm going to do a little port scan. Nothing wrong with the port scan. There's thousands of machines that do port scan on the network every day. Nobody is telling you about it, and it's fine. And then there is remote execution. So there is something which push from one machine to another. What we want to do is to be able to give you the way to trace that data back. We want to be able for you to do some forensic analysis. So what we've been, and I need to connect on that one. So once you found that initial weird activity, what we'd like to do is, that should be the one. What we want you to do is like, okay, what else has happened, right? Because as we don't have signatures, as we have behaviors, right? So one of the behavior is, I've got some strange tunnel going on, okay? Going to some Azure cloud or Amazon cloud. I want to be able to retrace that, right? What is the initial attack? How the malware was did propagate on my network? What is the IP address through that band? How do I, go through an analysis of that? So what we've been doing is just as we record every data, so to the question of, do you see the data? Yes, absolutely. We see all sort of HTTP traffic. We do some lookups for them. So here you see DNS tunnel, DNS activities, and all of the weird things you could imagine. We will store all things such as Kerberos tokens. So then you can figure out who are the accounts being used and so on, and you see things like administrator, that doesn't really look good. You will have NTLM, RPCUs, and things like that. What is probably more interesting is this type of things, right? If we have access to the HTTP traffic, you're able to really get things into the data. And probably that is a bit more worrying. So whenever you see things like PowerShell going out directly, it's never really good news. Most of the time it's pen testers that do that. The more advanced hackers, they will probably hide themselves in a much more clever way. But yeah, things to be concerned. Also, we will have all sorts of LDAP connections. So let's say, as an analyst, I want to understand, okay, who else is doing PowerShell on my network, right? So I just pin that stuff, and I want to discover on my network for all machines who's using PowerShell. So I've got all sorts of data that I can extract. So you mentioned, can you see files? Yes, absolutely. If it's using SMD, I will see every single file which is being transferred. Can I extract certificate out of it? Can I see SSH communication? Can I get? So we have a lot of things that we extract in the product. One of it being, in my case, HTTP sessions, when I will be able to retrace my PowerShell activity. So, okay, so there are many machines doing PowerShell. Let's see over the last months how it looks from a timeline point of view. Ooh, okay, so it seems to be something very recent. It started around here. I'd like to know eventually the name of the host. So we know that the guy was Jackson P. So here we go. I'd like to filter on Jackson P. And Jackson P is doing a few things. So outside of this traffic, what else does he do? Okay, so it seems that there is only traffic coming from that machine at that time. And then I'd like to eventually see the full URI. Then I'm able to figure out that there is something going on with that machine since quite some time. Right, so the idea is really to be able to trace back what's going on for that specific user. And eventually, if we drill down into the very first packet, we will figure out that there is an initial payload that has been loaded. The point is really, how do I retrace back the attack? How do I visualize the data in a way that makes sense for an analyst? Right? So that's kind of an intro. I will go down a bit into a deep dive of PowerPoint. Here we go. or what really we do in the background, right? So I guess we are about 45 minutes now in. So what makes us completely different in terms of how we do things is that. Politely, we call them security researchers. They are just a bunch of hackers, right? Not the nice ones. I mean, not always the nice ones. I mean, they sometimes are nice, but I don't want them on me. There are people that tell you interesting stories on how they've been asked at some point to hack, I don't know, some organization, and they figure out that probably the best way and the most silent way is just to get into the switches and just do DNS redirect to them. So every corporate traffic will go to them. And then they can filter out who they want to infect and how. There are people that will tell you how they went into some organization finding the 100 most critical people for that specific country and eventually managed to dump all of these guys within like 2 or 3 hours and getting into crazy databases that they shouldn't have access to. Asked by their governments, right, from all different countries, right? But that's the type of people, very specialized and very elite hackers. What they do for us is they hack into things. So if I look at the moment, the different activities that we have, it's like, if I look at cloud, there are very few people that have done proper research on cloud security, like fundamental research. What are the potential attack surface, the attack vectors that hackers could use to steal cloud-based stuff? Before they were doing this fundamental research that I mentioned on printers, for example, all these type of things, right? So what they do, they hack into things, and then they were like, oh, we see a very common pattern in the industry today. These specific tools being used, or techniques being used, more than tools. And then these techniques are being used in a certain way. So and so they write their own command and control activities. They write channels and stuff like that. And then they provide this information and this network traffic to our data scientists. What the job of the data scientist then is, hey, I will identify what is unique about that traffic. I will identify what is eventually the common part of all of this command and control traffic. So I would be able to, next time there is a command and control activity, to identify it without any question. Right? So the focus is like, okay, there are always common techniques that can be used. And so that's going to be the focus now. We eventually have a very limited subset of features in the product in terms of detections, right? Because as I said a very kind of quickly in the introduction, our focus is not to find everything, it's to find the progression of an attack. It's to find these key moments when the user is going to move from one machine to another. If you want to run an exploit against a machine, we will never alert you about that because there are exploits going out every single day. Looking for exploit and always trying to find a way to solve the exploit is not something that is sustainable. Looking how people progress and what they are looking for, like account thefts and all of these, is much more interesting and relevant because you don't have to hunt for this kind of 0-day new things going on that you need to patch always. So we came up with that list of activities that we believe is meaningful. And in order to get there and to create that list, we go through an interesting process, right? Which is, we get the data samples from our hackers. They come up with advanced attacks that are known or unknown in the market. We abstract that with and make a theory that all the tools are working certain ways. For example, we identify that remote access tools have 3 different ways to behave. One of the ways, and that's the case of Metapredator and Metasploit, for example, it's one session that is established from the machine which is infected to a command and control. And it's a long TCP session. You have tools like TeamViewer or these type of tools. What they do is you've got mouse and keyboard access. So the patterns that it defines on the network is very strange because every time you move the mouse, there is different feedback and a different kind of screen feedback coming back to you. So we analyze that, not looking at the data, but looking at the network flow. And we identify this behavior. And then we create a kind of database of false positive and negative to train the mathematical models. Then we give that features out to the data scientists, and they come up with a theory. They refine their model. They create, and we have a list of trusted customers that we work with today, to which we give them our theory, we install them on our product. We get feedback on what has been observed on live traffic for many customers. It's more than 120 today. When we just deploy on live data, analyze the results, improve the algorithm, and then we start to think about how you're going to use the product. Let's think about the design of the UI. So for you, when I show you that data smuggler activity, when people steal data from one place and send it to something else, it makes sense with you not having to think about it. Then we create a UI out of this concept, and then we check back on the efficiency of the algorithm on a regular basis. So for example, for the command and control, we always have a data scientist looking at it, always improving it, and so on. Then come many, many questions. Yeah, sure. What is data science? What is artificial intelligence? What are you doing so different, and why you think you're good, right? Plenty of questions that I will kind of try to answer. So this presentation was done by one of our lead data scientists in one of the biggest data science kind of colloque or whatever is the name of meeting, where they all meet together and tell how they use AI to do some cool stuff. So I've done that from him. And what is interesting, right, is if I look at the story and a bit back of the story of data science, the technique that we use today, and data science and artificial intelligence, come back more or less 60 years from now. Alan Turing eventually had some concepts, and then the techniques that we use today, this notion of neural network, which is like the voice recognition from Google and all of these, are things that are there since many, many years. What is interesting is we always try to improve on these specific algorithms, right, and these ideas, because there is never a perfect way to really solve a problem, right? So if I look at the different algorithms that exist today, they are like kind of an evolution of the different techniques to what we call deep learning today. So deep learning is a technique with a very limited amount of data sets and sample of data, where the artificial intelligence is able to extract, what is, the common features on its own, and then able to find new things based on this feature that they self-extracted. There is a very interesting talk from Google that explains that in their speech recognition software and this AI that they have today, they are not able to understand what they do. If I tell you today, does the voice recognition of Google works? Pretty well. I don't know for you, but it's fair. If you're English, it's perfect. What is interesting is they have no idea why it works. And they expect that in 20 or 40 years from now, they will be able to understand why the machine works that way. Because that self-learning and this self-establishment is something that we know what we give, we know the results, we know it computes something in the middle, but we cannot know why. We cannot predict how. We just need to rely on there is some data in, some data out. In between, the system figure out how to adapt itself to find the perfect solution to a problem. And if you look at every single AI tool or stuff that has been developed or which is developed today, nobody knows why it works. Scary when you think about self-driving cars and all of this, right? So what is interesting, right, is the notion of AI is automatic pilots back in like 50 years ago were considered to be, AI. Eventually today AI is more assimilated to deep learning or machine learning, where eventually what you try to do is you try to identify that. What does that mean? Well, probably it's very simple, like the cat. But here, it's very difficult for the machine to identify what that is really, because the machine is going to abstract different things and just say, hey, that's a T, that's a weird letter, that can be a A or H, that's a E, a C, and an A or H, and I will give a probability out of it. So you most of the time need to have multiple set of algorithms that make sense of the potential letters, and otherwise link it to the context. And this is what is super difficult. Finding anomalies, finding baselines, and so on is actually very easy. I'm certainly not an expert in data science, right? I've actually have a very modest mathematical degree. But eventually, the job now of a data scientist is, hey, I've got different data sets, right? I've got, a simple problem. I'd like to sort out the the blue and the orange. What I do is I've got my neural network, and so the library here is the one used by Google to do the voice recognition, right? So it's called TensorFlow. It's a very popular tool to do machine learning. And you've got this notion of neurons, which are like this machine that takes two functions, x1 and x2, different lines like that, and combine them together and weight them, and say, hey, do I see blue, do I see orange, and so on. And then whenever you train this machine, they are able, in a certain amount of time, to filter out the different machines. The job that we do at Vectra is to figure out, based on this good and bad data sample, what are the different functions that are needed to be able to qualify and how to separate the noise with the minimal amount of occurrences, to be the most precise and efficient as possible with the least amount of data set and the fastest as possible. That is our job. And the point is, whenever you start to have more complex problems, how many times? Well, 51 occurrences, I solved that problem. Well, pretty simple. How do I solve that? That's never going to work. The system is going to just fail. Let's it wait how it failed, right? So you need to find the right mathematical function. So here the classification can happen properly. This is the job of our analysts, to be able to have not a 50% false positive, because that would be a false positive case, but it's just like, okay, if I have more features in my system, actually just maybe more pieces of memory that are linked together, I should be able, after some time, to be better at filtering out the data. And then you get better, but it creates a lot of instability as well. Right? You cannot rely on having something like that. So then you're like, okay, that's probably not good enough. You have to think about, yeah, I'm going to re-inject some of the things that I've learned into that system. I'm going to add, actually, probably 2 neurons. And this is the job that our data scientists do, actually. Finding the right formula to solve the problem as efficiently as it can be done. Okay, so it's slightly better. It's actually more stable. We find more things. I think if we go with a smaller learning rate, different hidden layers, do we get better? So the difference between me and our data scientists is actually they exactly know which function to apply for a specific problem. And they also have the tooling to visualize the data in the proper way. Okay, so it's not going to be good enough, so it gets more features there. I think I don't need as many layers of neurons. Here you go. And eventually, after 6 months of research, you're able to find the perfect algorithm that should solve most of your problems. So before we had no coverage there, and then it's better. We have a very low kind of 7% false positive rate. System is going to get much better over time. And so we do that. Whenever we ship a product to customers, there are half of the algorithms that are pre-trained. So whenever we ship some of our products, like, hey, here, whenever we see some remote access, we figure out that all the orange is a remote access, all the blue is like normal traffic. We ship to you a machine and a brain and a network of neurons, which is much more stable than I just did, right? But also it's something that can see minute one, day one, malicious activities. And I don't need to relearn from your network that stuff. Things like who is the administrator, connecting to which services and so on, are things that I will learn locally on your network. There is about 50-50% of what is already learned in the product and what we actually has to be learned in your network. Make sense? So we don't do magic, right? We've got data, we try to find a nice way to visualize it, and eventually the half the job that we have is, it's very simple to say, well, we're going to do neural networks for everything, but eventually it doesn't solve really the problem, right? Like that's one technique to solve a problem, but the problem is really, and the statement is really, what do I need to have, and what is something that I can classify already, or I can supervise and say, hey, okay, based on how the animal behaves and certain set of parameters, I'm going to say, well, it's a cat or it's a dog, right? And you can make a statement, and you can have what we call supervised learning. So I have, based on the data set that I know and own, I'm able to define a rule. And I'm able to classify all sorts of dogs and so on. So actually, it's good parameters. So even so small dogs could be classified. There is a very interesting article of people that managed to find, based on the price of houses and how high they are from the height from the sea level, if you are in San Francisco and New York. Right? So they got people like are able to extract features like that to make some interesting analysis, right? So we have simple ways to do the regulation, like domestication and size, but sometimes you got to think about the problem in different ways. You need to find different representation of the problem and to reclassify them based on what makes sense. But you always have to visualize what's going on. On the opposite side, we get that notion of unsupervised learning. If I tell you, classify these dots here, we'll be like, that's a pretty tough problem to solve. Eventually, there are clusters and the system will learn about this cluster, about like who is the admin of that machine, how risky is that machine. And that's the second part of what we do with unsupervised learning. The challenge really for us is like, if I look at that kind of data sets that are kind of rather simple, if I look at the normal height of an NBA player, for example, you've got some people, and the average size of a player is like about 2 meters high, and some guys are 175, right? That's an anomaly, right? It's part of a distribution. So that would be eventually a false positive. When with Vectra, what we try to find is like the real bad guys, right? So the question is the notion of the data set is super important, right? The quality of the data and the features that you have to extract and what you're looking for is critical. So is the height of an NBA player qualify an NBA player? Probably not. Maybe the shooting ratio is a much more interesting feature to consider, right? So that's the idea here. And there is no perfect way, not a single algorithm that solves the problem with the right feature to solve the right problem. That is actually the only thing that is the problem. So we need to extract the bad activities, right? Security researcher job. But then you've got to find what works best for each of the problems. And I mentioned before this list of all of the behavior that we identified. For each of them, we have one to many specialized algorithms that solve a problem. What is a port scan? What qualifies a port scan? What is a malicious port scan compared to a normal port scan? The notion of malicious port scan is strange, right? It's like, if I'm a bad guy, I will not know your network. So whenever I scan your network, I will have a very high failure rate compared to I'm a software management tool and I'm scanning all of my machines and every single time I touch them. So what we have is like, we look for the malicious behaviors, we look for the malicious port scan, kind of, or the suspicious port scan, more exactly. On like, well, there is a lot of failures, so that guy doesn't know where he is. It's probably bad. So that's the type of problems that we try to solve, right? So I'm going to go a bit faster there because I don't think it's that important, and I'd like to go directly to a very precise problem statement, right? And a clear example and description of one of the algorithms we have, which is the remote access one, which is one of my favorites because over the last 7 years, we've been evolving that algorithm a lot. We use different techniques, different features, we look at different ways to this problem, and that's kind of the status of where we are right now. As an attacker, I will very likely never go directly to a machine and hack it like that. Because there is a firewall, because there are things like, actually, there is firewall. So I will be blocked. So I will find a way to hack that person, and that person is going to connect back to me. So as a hacker, I've got my command and control server, and I find a way to get the person that I've attacked to connect back to that command and control server. There are very well-known tools that does that. Some of them are eventually bad. Some of them are good. Why, as a hacker, should I use something which is like a crazy tool when I've got already LogMeIn installed and I've got the access to LogMeIn? Right? It's the prime statement. So if I look at that specific problem, so we look for all connection from user to the external services. And what we figure out, and I don't know if you remember that the network trace I just showed you before, and that very weird PowerShell activity, even if the traffic is unencrypted, you cannot make sense of what it means. It's not like you have the command line being sent and something bad happens. Like, there is that weird cipher stuff ongoing. So if I look at how a signature was done before, it's like, oh yeah, you go to that website, and then you have to go with every single website that can be potentially queried to find the bad guy. And that can create a lot of false positives. Eventually, that will not work whenever you have an encrypted traffic. So that cannot be sustainable. The way we approach the remote access is a very different way of seeing that problem, right? The first thing we did is like, well, maybe the people that goes into, that do remote access are people that goes to, this, or people that reach that hacker website, actually probably like, it's very rare. And then we extracted the network profile of our customer. And these are, so based on the network ports and based on the domain rarity. What we figured out is there is a lot of stuff going on port 445 or 443 today, so SSL encrypted. So we cannot rely on that. And this is the way, how often you see certain URLs. And as you can see, most of the URLs in an organization are seen like a very limited amount of time. Like I think here, all of this traffic is seen at once and at least less than twice. I think it's at 50%. So you cannot go with that rarity idea to solve the problem because then it creates a lot of noise. So instead, I don't know what you think, but I think it's pretty clear that it was not possible. So what we did is we look at the traffic and the traffic pattern from the host to the client to identify that there is this weird connection ongoing. And like that, then we are able to make an analysis on saying, hey, actually the first way we did it was analyzing, different attributes, and I cannot give you the detail of that because that's for sure intellectual property, right? To classify, the speed of the traffic and how good it is and how long it was and the amount of traffic generated. So we would classify it would be a CAT or remote access or a normal traffic. And at some point, whenever our algorithm figure out that, it's probably a CAT, we just, or remote access, we would just say, well, random forest, which is the technique that we use, was not the best one for us. So we started to go with this deep learning thing that I just showed you and I gave you in a demo. We figure out the number of right layers or middle layers to adapt, the features that we need to integrate into that algorithm, and the expected outcome, right? The most trendy technique that is being used today is neural networks. There is a specific subversion of the neural network called long short-term memory loss ones. So more or less the idea is you have a self-awareness of what has happened before, and what all of your little colleagues and your neurons are doing around you. And you share this information from all the different neurons. So that's you get some, where I'm input, my input gets. You get some information as well from others, and you forget something, so there are internal loops. And the idea is that you're able to detect some activities. So we eventually came up with a very extensive workflow of things, that how we conceived it. We started to think about the different representation and how the network behave based on the type of traffic being observed. We extracted all of this traffic. So here you've got some SMTP, and so here's some NTP. So we figured out that the remote access was going to be around here, I believe. Just like, okay, so in terms of pattern, it looks very, very strange compared to others. And then we are able to develop an algorithm that says, here you have a remote access. So the job of our guys today is really to be able to find all sorts of remote access, good and bad. Sometimes I'm scared to see, for example, companies which are providing MRI machine or scanners that does a copy of every single patient stuff and they send it to their premise. You don't know why. You got things like that happen in the wild that are unknown, that are pretty scary. So part of the thing that we really are proud of is that part of this research that we do is that's what's the next point for my rat, right? But for all of the other analysis that we made, sometimes the product is not perfect, right? It will classify things in a way, and we always improve to make the right clusters to have the least amount of false positive visible. So we cluster the data right, and we make sure that you have always, you find the bad guy. There are plenty of techniques that exist today and that are in our product to classify certain type of things. Eventually, we selected depending on certain type of activities, certain type of algorithms. But more or less, if I were to summarize, is like, we always ask ourselves about what should be supervised against non-supervised. How do I have the least amount of noise possible? How do I identify correctly things which is not noise? Yeah, with the kind of right type of algorithm. That was of a short kind of summary on 7 years of work that we did. So I think we will just have a break right now, I guess well deserved. And then if you want to go deep dive into arctangent features of neural networks, I'm more than happy to discuss about them.
Thank you.
Thank you.